All right, class, this is going to be your demonstrations for 17.1 and 17.2, which are buffers and common ion effect, which are interrelated concepts. So first up here, we have some saturated NaCl. And how do we know that this is saturated? We haven't talked about this a lot, but this has been stirring for 25 minutes and there's still solid at the bottom. Therefore, regardless of how much agitation I, perform on this solution, there's a limit to how much NaCl can actually fit in this given volume of water. So common ion effect says that the dissociation of an electrolyte is going to be limited by the presence of an ion that's already present in solution. This isn't like a really hard concept. It's like, all right, if that ion is already present in solution, well, it's already kind of like nearing or is at its capacity for containing that ion in the solution. So we can easily demonstrate this one by essentially taking this concentrated NaCl, adding some to the tube, and then I have strong HCl in the bottle right here. Okay. So by the addition of HCl, which we know is very strong electrolyte, there is a lot of Cl- ion already present in this solution, but it's getting ready to be added to a solution that is essentially already at its capacity for Cl-. So let's take a look here. What you see is the tremendous precipitation of sodium chloride, which is very soluble compound, but it has a limit. And considering that saturated sodium chloride solution already is so packed with Cl- as is, the Cl- has no room left in that solution, precipitates out that NaCl, and that is my demonstration on common ion effect there. Over here to buffers. So buffers are a really important instrumental reagent in the laboratory. They help us calibrate our pH meters, but buffers are important all over the place. I had mentioned previously in class that buffering the mobile phase at a specific pH can give you access, or force your analyte to be in its more molecular or ionized form. Your blood is a natural buffering mechanism such that it can buffer out minor amounts of acid and base, and that's really what buffers do. They are set up in such a way that, again, give them the ability to handle, to an extent, minor additions of acid and base. So I'm going to start by putting this pH meter, which is calibrated, into some pure water, and then I'm going to add a little bit of strong base to it. Now, water is a terrible buffer. It really can't handle pH changes, right? The second you add, acid and base to water, the pH changes drastically. So I'm gonna put this pH meter in the water, and I'm gonna add a little bit of sodium hydroxide to it, 1 molar. And a few drops. And it is, again, majorly disrupted, skyrocketing, hopefully you can see, to 11.7. Now, alternatively, the buffer can buffer out the addition of this reagent, which I will demonstrate. So I'm gonna put this in my 7 buffer. Here you guys are waiting to come in while I finish my video. Okay, this one is, again, in the pH 7 solution. And I'm gonna do the same thing. Couple additions of strong base, couple drops. And no change, 0.1. So we said buffering capacity is limited. It's not infinite. A couple more drops here. And another point change, not even actually. But again, notice the difference. The sodium hydroxide added to the water skyrockets its pH to alkaline, but the same additions of the sodium hydroxide to the buffered solution have very minor changes on the pH, and that is what buffers do. That is your demonstration on both buffers and the common ion effect. Hope you're having a good day. Let's have a nice strong end to the year.